In the past weeks, we've discussed techniques, optimization, grid modeling, in order to control a grid by controlling generation and possibly by controlling batteries. And we've seen, I guess you are still in the middle of some issues relative to OPF, MPC, and the like. So those are the standard techniques that are used today to run the grid. On the generation side, now there is a set of other techniques on the consumption side, which is the topic of today. So demand response is when we want to control an electrical grid by playing with the demand, with the consumption. Like, for example, illustrated here, electric cars, heating systems, etc. So what we will do is first start with an illustration by examples. Demand response is a fairly new topic that is emerging now, enabled by the automatization of the grid and the fact that we have smart meters. We're able to talk to appliances in an intelligent way, which was not so easy in the past. So it is emerging. Like anything emerging, it's a bit varied. There are many different instances and proposals on how to do demand response that have been proposed. So we will go through some of them by going through papers that were published in the literature. Then, after studying those examples, I will provide you a few highlights on what I call elements of theory, which are the underlying theoretical understanding that we have of such things. About terminology, we find a bit conflicting terms. So demand side management, demand response are words that are used sometimes interchangeably, sometimes not. So in this talk here, I will always use the word demand response. Demand response, strictly census, means when we manipulate the consumption as a response to price. We've seen an example in the past week, in fact, when David's house is using an MPC to control his heating system and decides to heat more a bit before the high power price, so increase the inside temperature a bit more than necessary in order to save on future costs because the prices are increasing. That's a typical example of demand response. That's the goal of those variable prices. This is one of the main motivations to deploy smart meters, is to be able to signal to the appliances prices that are different, and also to be able to meter per time basis that are at a fine, small granularity, because the price will depend on time here. So that's demand response. Now, there are other forms of similar way of achieving the objective, not by a price, but by other mechanisms. For example, an electric utility might directly manipulate your appliance. We will see examples of this. So here, there is here a box that the electric utility sends a signal in the electrical line that switches a relay that disconnects, for example, your washing machine. So whether you would like it or not. In fact, it doesn't disconnect the washing machine. It disconnects the power socket on which the washing machine is connected. So that's called demand side management. But that's a subtle difference, but in the literature, we'll find sometimes this difference. I mentioned that this is new, and it's true that in the current form that we will see in the papers here, and the amplitude that it has is new, but it has been around in many countries, in Switzerland, in France, in other European countries. It has been around for many decades under the name of sometimes called ripple control. Ripple control is exactly what I mentioned here. And it's still visible in Switzerland if you have an electric boiler. Very often the boiler is controlled, is on a special socket. So in many houses that use electric boilers, you have two different types of sockets. The one that are controlled, that are allowed to run only at some point in time under the control of the utility, and others that are not. Of course, for the beamer, the computer, the TV, the lights, they are not controlled, but the boiler is controlled. How does this work? Well, you can send in the electric lines, you can send extremely low frequency signals that are called ripples. A little noise, if you want, you send a little melody that is encoded at a few hertz. You can, so by doing that, you slightly change the form of the signal. And if you have a PMU where you're analyzing the signal, you should see that form, at least if you have a PMU that's able to see many, many different frequencies. And that is captured by a box. Essentially, you send a beep to a box. When the box has two types of beep, a beep on and a beep off. When you send the beep off, then the box goes off. Why was this used? Well, this was used when countries introduced, for example, nuclear energy. So all countries that have nuclear energy have the special feature of nuclear energy, apart from all the dangers, risks, etc. But from a power generation viewpoint, it has the feature that it gives constant power until it's shut down for repair or maintenance or accident. But while it works at constant power. The only way you can modulate the power of a nuclear plant is by curtailing some of the energy. So you release some vapor into the air, so you throw away the heat produced by the nuclear power produces heat, that's all. Then you use the heat to have a big steam engine that produces electricity. And the only way you can control it, not the only, but the major way with which you can control it is really by controlling the production of electricity by throwing away some of the heat, which of course is not a good idea. So you would prefer not to do it. It's very hard to control at a very low, like you do for a battery, for example. It's hard to control the nuclear reaction itself. So nuclear, and in particular, you will not shut down at night the nuclear reactors because there's less consumption at night than during the day. So the nuclear reactors, once they start working, they work for several days. It takes several days to have them up and down as well. So you have a constant production of energy in many countries that have used nuclear energy. And the problem is, what do you do during the night with it? So one way to do it is, well, you heat your water in the boilers during the night. That's what we do in Switzerland in many, many places. So with the side effect that if you're in a colloque and you're 6 people taking a shower, perhaps the 6th one has no hot water because the hot water is only replenished at night. That's exactly the world of demand response. So we have already a first impression of it. And now this is what is going to become much more flexible and much more widespread in the future. So to finish my introduction on demand response, let me test you on what you think the goal of demand response in reality is. I close the poll in a few seconds. And the majority says C, which is probably exactly what is expected. The issue is really that electric systems must balance power instantly. In a grid, I mean, the very special thing about the grid, which is not true of other energy systems, like a gas energy system, has some slack in the sense that you have some buffer in the tubes themselves. Now, the buffer that exists in the electrical grid is quasi-null. It's not exactly null, but it's quasi-null. That means that at every point in time, when you change the consumption, you must also change the production. Right? So when I power on my kettle to boil some water, there must be somewhere an increase in production that comes at the same time. That's the fragility, that's the problem with the electrical grids. We can solve that with a number of mechanisms, and what we will discuss here. But that means we constantly have to adjust supply to demand. And what we have seen so far is how the supply can follow demand. You can follow it by having a number of mechanisms that we will discuss at a high frequency, at a small time resolution. What you've seen in the labs is how you can follow it at, I would say, resolution of several minutes by doing an MPC and measuring or forecasting and measuring. We can have batteries, for example, that will adapt the consumption. We can also, of course, use demand response for that. And that's the main goal. Of course, this is, as I mentioned, in the past, the problem was more, we have constant power generators and we have variable consumption. But the variability of the consumption is, as I mentioned several times, is relatively small. So the goal of demand response in the past was essentially to shift the consumption so as to balance, put more consumption during the off-peak hour. That was the main goal in the past here. As we will see, there are other goals that we'll discuss in a second. I still mention energy efficiency, which is often confused, and we will see in some of the papers that I cite, we'll see that this confusion is sometimes introduced on purpose. Of course, when we start managing an energy system, typically we also improve efficiency. If you have a stupid resistive heater and resistive convectors for heating your house, probably you're totally inefficient. If you start introducing some intelligence in the system, you will practically automatically gain some efficiency. For example, by having adjustable thermostats that can be controlled remotely, you will automatically save because you will discover there are some rooms that are not used. Perhaps you have a room for gym that's never used in the day, only in the evening, so you don't need to heat it up during the day. So there is usually, as a side effect, an energy efficiency. But per se, as we will see, it's not the goal of demand response. And that's one of the questions that we will ask about demand response. Is it really introducing energy efficiency? Here is one of the main goals of demand response that probably will be, you will see actively next winter. It's called peak shaving. So this is the consumption of a typical week in November. November is a typical bad month because it's gray. There is not quasi zero, but very little solar energy. Now, solar energy is today in countries that have some decent deployment of solar energy, like Germany, Switzerland, not so much, but Germany, France have a bit more, then it is perceived as a negative consumption because most of it is not really installed in big power plants, but distributed on people's houses. So it feels like negative consumption. Now, in the month of November, December, when there is less of it, then it is as if the consumption would be increasing. It's also increasing because it's dark, although light is not so much of a consumption today, thanks to modern LED technology. But also it starts to be cold and humid, so people start heating in these parts of the world where the main concern so far has been cold. And the result is that that's one of the fragile months of the year. It might be November, it might be February, it depends on. And next year, because we know there are tensions on the primary energy sources, gas and oil, are going to be perhaps in short supply, there might be some concern here. Now, this is showing the loads on 2 typical days in November. The darker blue is on a cold day, and the light blue is in average in November. So the first thing you see is the immediate. Now this scale doesn't start at 0, so the difference is not as large as it seems, but still the difference is not negligible. You see that the weather has an effect. That's the first thing you see. That is easy to manage, at least to forecast, because weather at this time scale is relatively easy to forecast. You know 1 week in advance whether it will be colder. You don't know exactly whether it will rain during your barbecue event, but you can know that the temperature will be low, so people will heat more. So that's not so much of a problem in terms of forecasting, but that causes a problem, which is shown here. That's the peaks. The load is not constant over the day, but varies a lot. And here, that is typically the evening peak. When people go home, they start cooking. Perhaps they heat more their house because they've been away most of the day. So there is typically a peak. There's one in the morning and one in the evening here. And as you can see, there are auxiliary ones that may have to do precisely with demand response here. So these peaks are the major problem. you need, because as we have discussed, you cannot store electricity in the grid. So you can store it in batteries, but you need to have batteries that are deployed here. So you need to produce exactly that peak power for essentially very few peaks in the year. First, it happens only in the cold months, and it happens for very short periods of time in a few days of the cold months, and only on the cold days of the cold months. So if you compare the peak here to the peak there, there is a difference of 1 terawatt-hour. That's exactly the problem of the energy system, that you need, if you don't want to have blackout, you have to have the capacity of a system that's engineered for the peak. And that's extremely expensive, and sometimes you cannot. And probably next winter, most countries in Europe will not be able to sustain the largest peak because there will not be enough gas flowing into the system here. So one of the possibilities that we can do is to use demand response by asking as many devices, appliances, customers to reduce their consumption during this peak. That is one of the major concerns. It's called peak shaving. It is so much of a concern that the tariffing of electricity is changing, is transitioning from a tariff today that's essentially based on consumption. We pay per kilowatt hour consumed, perhaps as a function of the time of the day, as we will discuss. But in addition, what is becoming new now is that we add the concept of peak power pricing. If you want in your house to have so many kilowatts, for example, of peak power, you'll have to pay a subscription that is much more expensive if your number of kilowatts is very expensive, which means that if you have, for example, an electric car, you want to charge your electric car, and if you want to buy a subscription that allows you to charge your electric car at full power without solar panels at any time of the day, then you will pay a high price for that. And the reasoning for that is that by having this peak potential in your house, you create the need for the grid to be able to sustain your peak and the peak of many people like you. If you buy a subscription with a much smaller peak, then you make things easier because we know you are limited by the peak power that you have in your system, which might incentivize you, for example, to complement your system by solar panels. If you want to charge your electric car very fast and you have solar panels or a battery also that many people start having, then you might use your own resources to reduce the peak here, thus mitigating some of this problem. Question?
In practice, electricity distributors, to put this into practice, they just plug the electricity on your line and with a switch once they count that you've went up this.
Or you have a max fuse or a switch that will simply disconnect when the power becomes. In fact, you have that today. You have, for example, on your line, you have a given line, you have, for example, maximum 16 amps. If you exceed the 16 amps, then the line will trip.
But here it depends on the hour. Like you were saying, we have a contract, for instance, where.
No, what is on the, as far as that may come, I'm sure you can do smart electronic that will have a tripping power that depends on the time of the day. I think the practice I've seen today is you have a max power. That's the price you pay for. That's your peak power. And that is static, or at least changes when you change your subscription. And then what the smart meter does is the tariff. You pay per kilowatt hour at a price that depends on the time of use. So we've discussed peak shaving, which is has to do with the capacity of the grid. But there are other reasons for that, for doing similar things. It's also response to failures. Imagine one big generator, for example, in Switzerland, one major dam, a barrage de Dixence, has a problem. We need to stop the turbine. Or more frequently, nuclear powers, nuclear plants. As soon as you know, nuclear plants have very stringent security measures. So as soon as something is suspicious, you try to stop it, which means that nuclear plants are very often stopped. Then if you lose a big nuclear plant of a small one would be 0.5 gigawatt, a big one 2 gigawatt, then it might, if it happens during one of such instance, that might be a serious problem. In such a case, you might ask people who have flexibility to reduce their power. Of course, we will see there are other mechanisms, but that's one of the dimensions we can use. But more importantly, and the reason this is gaining importance now, is the volatility of the renewable energies. In particular, the wind energy is hard to predict. I mentioned that several times. It's not impossible to predict, but the accuracy of the precision is typically less than for other renewable energies. Solar energy is much easier to predict, but still is variable in the sense, even if you predict that there will be zero sun in the next 10 days, well, there is zero sun, and then you might have a problem when you combine peak consumption with loss of solar energy. So the more renewables we put into the grid, the more variable we make the grid, and the more we need mechanisms to mitigate the variability. So that's really the reason why demand response is booming now, while there are so many enterprises and so many services, I will describe a few of them, that are emerging now. You may also have, so what we discussed so far is the supply problem. The fact that we need always to generate as much as we consume. But we've seen in the labs and in several of the examples, there might be other problems. Voltage, which is one of the topics in the lab, that happens typically when we have very large loads. Today, that is due to electric cars, also sometimes heat pumps. But also too large production. When we have solar panels, we can and we start to have in some places the converse problem. When you have solar panels, you install them to work for the whole year. In this part of the world, we need more electricity in winter. So if you dimension it to help really the grid in winter, what happens in this period of the year, when end of May, June, where the solar production is maximal and the consumption is not very large because we don't heat. And here we're fortunate enough, we don't air condition either. So the consumption is reduced and the production is maximized. And there might be excess. Excess might mean over voltage in the distribution grid. Because the distribution grids, they were not necessarily made to support such high power flows. We will not, when you build a new neighborhood, you build a grid that's able to sustain, you imagine there will be solar panels and electric cars. But when you live in a neighborhood where the grid is already established, then you will not rebuild the electrical grid, will not change the lines and the transformers. Instead, you will do things to control the voltage, like we did with batteries, for example. We did it to sustain voltage drops in the lab. You can do it the same to sustain voltage excesses. For example, having batteries embedded in the distribution grids to absorb the peak generation of solar panels. That will happen in May and June, because even in May and June, there is some night, right? The solar panels don't produce during the night, so you can absorb it during the peak of the day and release it during the night. But if you don't have enough batteries, you may also do some demand response on the user to consume more, for example, or even curtail the solar panels. That's one of the dimensions that is often discussed. So I've given already some examples of what can be subject to demand response. Of course, what can be subject to demand response is what is called elastic loads, loads that can be deferred or modulated. We think of loads typically as not being elastic, and certainly lighting, the lights here, the beamer, TV, hair drying, those are things probably you don't want to defer. But there's a number of things that can be deferred or can be modulated. For example, charging your car can be done probably in many, not always, of course, but in many cases you have some flexibility. You can charge it at some point between your arrival home and your departure the next day. So you have, if it takes 1 hour to charge your battery entirely at max power, but you have an available period of 8 hours, then you have some flexibilities here. And there, as we've seen, boilers, heating systems, and the converse of heating systems, cooling systems, freezers, air conditioners, sometimes even washing machine. If you have a washing machine that not the one that is in the shared washing machine in a Swiss apartment building where you can use it during a certain time slot. But if you have a washing machine with more flexibility in your own house, for example, you could start a program and let the program run. If you wanted tomorrow morning, you can choose the time of the night that is more convenient. So demand response goes with elastic loads. Lots of loads are non-elastic, or even elastic loads are not infinitely elastic. So of course, we can always combine this with batteries, but this we've seen already before. What I will go through now is a few examples of pilot runs, so things that are working or have been working in various places in the world here. The first example we saw is an MPC to control your house, right? So this is coming. I would say it's not hugely widespread. There are a few places in the world where individuals have variable tariffs. We've seen that in Texas a few months ago when there was a blackout, a collapse of the grid, and then the remaining parts of the grid that were working were offering prices that were incredibly volatile. When we mean incredibly volatile, that means the price of electricity was multiplied by a factor of 100, for example. So all of a sudden, a kilowatt hour costs not 20 cents, but 20 francs. So, and people were charged on real time on their bank accounts, so they saw their hundreds and thousands of francs going away from their bank account as they're automatically controlled by their smart meter. So that's the liberal view of smart meters. Here is an example, a more, I would say, social democrat view in Norway, which is, so to conclude on that, in Europe, there is a lot of reluctance to do it in such a brutal form as was done in Texas, for example. But companies have that type of contract. So if you have not a house, but a campus or a big industrial building, you will typically negotiate a contract that has variable prices and flexibility, because the prices, the integral of the prices will be less in general when it's variable, but you need some intelligence to manage it well. If you have variable prices, but you live as if the prices were not variable, you're taking the risk of having huge bills at some points in time because you're not reacting flexibly. So you need things like MPCs and so on, which are seldom done for individual houses, but are typically done for large industrial equipment here. But here is an example that was deployed in Norway to incentivize people to use high tariffs and times. High tariffs to have variable prices here. So what they did is they monitored a number with smart meters, the consumption of a number of users, and users had a variable price here that is shown here. But the difference to Texas is that you were warned that the period of high prices were given. So the high prices were the morning peak, 9 to 11, and the evening peak from 6 to 8. So you knew, if you participate in this tariff, you know that at those points in time, electricity might be expensive. Must not be expensive, but might be expensive here every day. And the result, and people were incentivized or were made aware of that by putting stickers, for example, on the washing machines and so on. So now before you start washing, if you start at 6 o'clock, then you're remembered that this might be very expensive. So perhaps if there's a timer on your washing machine, you delay it by 2 hours or you do it later. So they tried this and they concluded that it worked, that incentivizing people had a significant effect. So here we see the peak, the two curves. The top curve is showing the peak before the study, and the lower curves here shows the value after the study. And we see here the effect here. Sorry, that's the price signal, the value of the price here. That's the value of the price. And now this is the profile that results from deploying such a price. So the green dashed line is what people were doing before, and the blue line is what they do now here. So we see there is indeed a reduction. We see also something interesting here is that the reduction tends to evaporate at the end of the period. So people are willing to stop, but 2 hours perhaps is just the largest time they are willing to delay here, because we see that at the end of the 2 hours, there's already a consumption that's increasing. In fact, if you observe it clearly here, you see something interesting here, which is called the rebound effect, that you have incentivized people to consume less now. What happens is they consume more after. So when you engineer this as a utility manager, you have to be aware of this. Of course, you will reduce this thing here, but you might increase it after. So if you don't have enough capacity after, that might be worse. Now, the main reason for doing this was that inside Norway, there was huge price difference. So Norway has introduced locational marginal prices, like we saw in the lecture. We can calculate as a function of the capacity of the grid and of the consumption. We can calculate the locational marginal prices of electricity. And because Norway is a very long country, one-dimensional essentially, the grid is, in every long country, the grid is always a problem. You have a country that is very round, you have a lot of parallel lines, and the grids can easily be more resilient. When you have very long countries like Canada, Norway, Argentina, then you have more problems. You have to do very, very long lines. And if the line breaks, there's a problem. And also the capacity of the line, of course, becomes the limiting factor. So you had this, you saw that in two regions in Norway, there were different prices at different times of the day. And precisely, there is the evening peak, where in one of the regions, the peak was very high. Because in this region, probably, there is a lot of consumption and not so much production. The production comes from the rest of the country here. And then they claimed that the price peak would be suppressed, at least by simulation, because they did not get really the prices at this time, but this was later confirmed that in fact this price peak could be suppressed by demand response here. Simply by manipulating people to behave a bit differently, we can manipulate the prices here. And the argument they give for this manipulation is this curve here that we will explain a bit later. These are called demand curves here. So this is showing the demand and the effect of load shifting. We will discuss that a bit later when we come to the demand and supply curves here. But in a nutshell, as we have seen in the lab, the locational marginal prices depend on the consumption here. If you decrease the consumption at a node, you might dramatically decrease the locational marginal price in the case where the excess consumption had to come from another part of the country where you would pay for losses, and perhaps also because you need to have peak generators that are more expensive. You see here that the price amplitude is large. And as we've seen in the example of Texas, there were other examples in New Zealand and Tasmania. This is not large for price amplitudes. When the price amplitudes, when we introduce variable prices, and with this type of a pricing mechanism that we'll discuss, can be huge, can be much, much worse than that. As I mentioned, a factor of 100. Here we have a factor of 5 or 6. But it can be much worse here. Yes?
Don't you risk like a major migration of the population in the area where prices is lower? Because I mean, in Norway, for instance, you say there is no generation part of the country.
I do not say there's no generation. There's probably less generation relative to the population.
We don't have that much sun in this part of the country, so it might lead to migration.
In extreme cases, but I think in Norway it won't. I mean, first, such a price is probably not justifying that you migrate, because during 2 hours of the day, the price goes from 20 to 160. I mean, it's easier to do demand response than to migrate, first. And second, Norway has a lot of hydro. So it's more a capacity issue than a fundamental physical issue. And it's probably more the grid itself that is making it impossible to shuffle the power that would come from the areas where it's available. So you need to have local probably gas power generators that are locally helping the grid to prevent congestion. That's probably more what happens. In other places of the world, you might migrate because of that, but there are technological solutions to avoid migration if your problem is electricity, right? At least in many places in the world. More recently in Switzerland, we have similar things. For example, you can have what is called time of use tariff, where the night tariff is lower. That's what I mentioned for your boiler. If you have a resistive boiler, that's typically what you will have. So you will pay a bit less for your boiler if you allow it to be operated at some points in time, which can be static or, as we mentioned, interruptible. And here, for example, Romande Energie, which is one of the local providers in this region, provides two types of interruptible supplies, short or long. Short means that's typically for boiler. We guarantee to you that your boiler will work 8 hours every day, every period of 24 hours. But we don't tell you when exactly. That's exactly the boiler example I mentioned. It's typically at night, but when it starts is under the control of the energy provider. We know it will be at night, but whether it will start at 11 in the evening or at midnight or at 9 o'clock is under the control of the operator based on the operation of the grid. Because we know, of course, when we start this, the demand increases. Also, the operator has the possibility to stagger the different boilers. Not all boilers need to start at the same time. So if you're Romande Energie, you don't send the signal to all parts of your grid at the same time, so that you can have a ramp that is smaller here. That's typically for boilers. And you have, for resistive heating, that's typically what you have if you have old technology resistive heating, like you have typically in a vacation house, where the investment of making an MPC with a heat pump and so on is probably too large. So instead, you use a system like this, where here the interruption is 4 hours every day. Here we were saying your boiler can work 8 hours every day. Here we say your heating system can work 20 hours every day. We can interrupt it by at most 1 hour, at most 4 times every day. So when you're in your chalet, the heating may stop during 1 hour because Romande Energie needs to reduce the power to peak, to shave a peak, for example. So those are examples that are, I would say, using traditional technology where the user has no control. It's all the utility that manipulates by interrupting the supply. Instead of, in contrast with this, where the user had some control because we knew there was a high price here. You can still use it if you want, or you can defer, but it was up to the user to do it here. So demand response is related to other mechanisms of control of the grid here. As we have mentioned, the grid must maintain the power balance quasi-instantly at all time scales, quasi at all time scale here. Now let's discuss again more in detail how this is done. I mentioned that when I start a boiler, or I want to boil hot water to make a tea, then there must be somewhere more generation that is produced here. How is that coming? Well, the first thing that comes is the mechanical inertia. 4 grids that have mechanical inertia. So what is mechanical inertia? Well, if you have a nuclear plant that has a big steam engine with a big rotating rotor that generates electricity, that's a big rotating mass. It has an inertia. If you pull more energy from this big rotating mass, it will slow down a bit. It's the same mechanism that if you're on your bicycle and you are happily going down the slope, and then the slope changes and it goes up, then your bicycle will continue going up, but will slow down. So by continuing going up, it returns the mechanical energy, the kinetic energy, in this case, that you had in your bicycle, is now used to go up. Exactly the same thing happened. This big rotating mass is rotating. If we pull more energy, it's like putting the brake on the mass. It will slow down, but while slowing down, it returns some of the kinetic energy, the rotational energy that it has, and that will allow me to boil my hot water, at least for a fraction of a second. Of course, if nothing else happens, it will slow down and stop, and the system will stop and we'll have a blackout. That's an example of the instability of power systems. There is at the microscopic level, there is some inertia that creates some stability, but as soon as we go beyond the microscopic time scale, this goes into something where the only stable point is there is no power. So it is unstable from a viewpoint of the user. So this is why there is a second system, which is called the droop control. All those mechanical generators are equipped with a power law, a control law, a linear control law, that is implemented in what's called the governor, that essentially senses the rotating speed. The rotation speed is related directly to the frequency of the power. So we monitor the frequency, and whenever it is slowing down, then I put more gas. I was mentioning the bicycle. Now, if you're in a car, not in a bicycle, if you're driving at constant speed, if the car slows down, or if your cruise control will put more gas when you see that it starts slowing down. That's exactly what all generators do. So the grid code says if you connect to the grid a generator, you must do that. You must do that. That means whenever there is a bit more power that's being used, you should have some flexibility. You should not be always operating at your max power. You should have always a bit of flexibility. And you constantly modulate the power that you send into the grid by sensing the frequency. Whenever the frequency drops a bit, when I say a bit, it's by a fraction of a millihertz. Right? We're not saying of hertz, but fractions or millihertz. When it reduces a bit, then you increase the speed of your generator, you put more power into the system, and and conversely, if it goes a bit too fast, you reduce the power. That gives a first stabilizing element of the grid, which is called primary frequency control here. That's called primary frequency control. And this is why also we see that the frequency, I've already mentioned this, but that's an important thing to remember, frequency is a symptom of power balance in an AC grid. The frequency has a nominal value, 50 hertz in Europe, 60 hertz in some other parts of the world. If it deviates by millihertz away from 50 hertz, that's a symptom of imbalance. This is why often the services that are the control of a grid, of the power balance, is in fact called frequency control. So operators, energy providers, think of it as managing the frequency of the grid because their monitoring systems are tracking the frequency. But for us, the frequency has no holy values. It's not a sacred value. I mean, if my grid was working at 49 hertz, and if the power balance would be guaranteed, there would be no problem. Perhaps some engines that are synchronous would not be, some rotors would have a problem with their speeds. Perhaps some clocks that use the frequency to adjust the time would be slowing down, but most electronic and most systems would work perfectly well. So the frequency in traditional grid is a symptom of power balance because traditional grids have generation through big rotating masses. When we start going away from this, the frequency does not play this role anymore. There are already some examples of grids where frequency is no longer the thing of interest. There are a few islands in the world, for example, that live on wind energy and are complemented by batteries. So wind generators, typically the wind generators although they are rotating mass, but they are interfaced to the grid with a DC-AC inverter. Therefore, they are not, the inertia is not directly translated from the rotating mass to the power, to the frequency here. And batteries are the same. Batteries have no mechanical frequency. So if you have such a microgrid or the grid of an island where there is no big rotating mass, The frequency is entirely synthetic, is given by one of the DC AC inverters must play what is called the role of a grid-forming inverter. That's the one that plays the role of the slack bus. And in such a slack bus, the frequency is fixed, is given by the electronic, is not depending on the power imbalance. Power imbalance must be controlled by other mechanisms, for example, by measuring voltage at a battery and measuring power flows, simply. Typically also by having a battery that will play a role of a voltage source. By being a voltage source, it will automatically put more power when there is power deficits instead of reacting to frequency here. But today in continental Europe and even in the UK, in large countries, it is still frequency that is used as the symptom and must be controlled. So how is such a big countrywide and grid organized? Well, this is showing a map. This map is a bit outdated. There's a map of ENSOE. This is the so-called continental Europe interconnection. So continental Europe, that means most of Europe, and today it includes Ukraine, at least the part of Ukraine that is not destroyed and is working. And this is all interconnected in frequency. So when I say interconnected in frequency, that means that the frequency of this system is quasi the same. So there is a frequency solidarity here. All those systems are interconnected by AC lines here. It is also connected, for example, to the UK, but the UK is not connected in frequency. It's connected by DC lines or by other mechanisms that decouple the frequency. It means the UK is itself an island and has to maintain its own frequency. Ireland, the island of Ireland, is also another system. And the northern part of Europe, Scandinavia and the Baltic countries are yet another system here. They are interconnected, they can exchange power by DC lines, but the frequency is not interconnected. Now, frequency is interconnected, that means that this is like one big system. This is illustrating what happens, for example, when a nuclear plant is disconnected in France. So here you're showing somewhere in France, a nuclear plant, we lose, for example, 1 gigawatt here. Then what happens? Well, we see that on the frequency here. All systems in this interconnection will see it. So people in Romania, in Greece, in Spain, everywhere, they will see that the frequency is dropping. The frequency is not exactly the same everywhere, but is up to 1 or 2 cycles where you will see exactly the same pattern. So the frequency is dropping here. As you see, a drop of that amplitude is considered a large drop. So we're talking of really extremely small variations of the frequency. This is sensed by all the control systems in the area. But the first thing that happens is that because of droop control that we mentioned before, all generators will start producing more. And this will play a role here during the first 5 minutes. We see that all generators in Europe are producing more. Now, by producing more, they might not be able to recover the loss here of a big power plant here, but that mitigates the problem. So that's the first thing that happens. And that happens instantly and without communication. Of course, you need to engineer all your power generators. We'll discuss a bit more about that in a second. So every generator has some flexibility that it can provide. It can increase its power. And this is, you see, it's slowly ramping up, but with some difficulty. Then what happens is another layer of control, which is now using communication systems and explicit means, is called secondary frequency control. Secondary frequency control is per operator. When I say operator, it's transmission system operator. Transmission system are the operators that are responsible for the high voltage parts of the grid. There is one in France. There is one in Switzerland. In Germany, I believe there are several ones. So there is one or several per country. We mentioned their roles already in this course. The main role here in this story is to maintain the power balance of the grid by monitoring what happens. So now, in this case, the outage is in France, so it is the responsibility of the TSO, the transmission system operator, that is responsible for the area where the outage occurs, to call for reserves. And those reserves are called the secondary reserves. Secondary reserves, those are generators that are here in hot standby and that are able to recover to produce more. For example, if you own a gas turbine, imagine you inherited a few millions and you don't know what to do with it, so you decided to buy a gas turbine. Perhaps not such a good idea if it's not biogas today. And you wonder, what do you want to do with this gas turbine? Well, I could say, I could sell to Swissgrid or to the French TSO. You could sell a service where you provide secondary reserve. So in order to sell such a service, you will need to be qualified and agreed by Swissgrid, for example, who will verify whether you're truly able to provide that amount of energy on demand. And then you will be connected to a system of Swissgrid that will send you explicit messages. And within seconds, you need to start your generator, for example, and produce, or also reduce here. For example, that's a service that some we'll say some demand response operator can also benefit from here. So that's the second response that will apply. So first, the outage. Second, the whole of Europe reacts to the outage with primary frequency support. And then the area where the problem has finds some backup called secondary reserve. So secondary reserve is reserves that can be mobilized within seconds to minutes here. Of course, this is backup reserve, so it's not something that is able to sustain very long, so it will work for perhaps 1 hour or 2. If the outage is long enough, then you need to mobilize what is called tertiary reserve. So there are reserves that are able to work for a longer period of time to make up for the loss here, but those are reserves that may also take more time to start. Those ones are typically what is called spinning reserves. There are things that are ready to work within very short time. Here, those are reserves that may take hours, 1 or 2 hours to start, but that will be able to recover from this loss here. For example, in this case, there might be operators in France or even outside France that have a contract to provide such a reserve. For example, here we have a Spanish generator that had a contract with the French operator to provide some reserve to make up for this loss here. So this is how the grid works today. This is why it works. It works most of the time. We see that the global outages are extremely rare, orders of 1 or 2 hours per year. So that's, and the larger the system, then the better it is, because the inertia is larger. So even a big loss here can be already mitigated by primary frequency. Of course, if you have a smaller country like Ireland, which has a population of 6 million inhabitants and is an island, then the reserves is proportionally much larger than for continental Europe here. The UK, for example, is a smaller island, so the cost of reserves in the UK is much larger. So people have seriously considered using the fridges for primary frequency support. The idea is that a fridge is a thermal load, like David's McKay's house that we saw. A fridge stores cold, if we want, into its inertia, and it has also a temperature band. So typically it should be between, I'm not sure about the temperature, but let's say between 3 and 5 degrees inside for the non-freezing compartment. And the freezing compartment could be anywhere as long as below -21, it's okay. So you could freeze it to -30 and let the temperature go up. So exactly the converse of the house. You can play with the temperature if it is more advantageous to do so. Here, the idea was a bit different. You don't do an MPC. You simply install a chip on the fridge that monitors the frequency, the power frequency. So it turns out that this is not very difficult to do. If the only thing you want to do is monitor the frequency, in particular the variations from frequency, and then you can start with having systems that says that is the sophisticated thermostat control of the fridge, which is illustrated here, which says that whenever there is a control region, that means whenever the chip on your fridge has sensed that you have to help the grid, then you might decide to play with the on and off time where the fridge is working. So most fridges work by being on off. You start the compressor, the temperature drops. When the temperature goes below a threshold, you stop the compressor, the temperature will go up again, and then you will start the compressor, like the thermostat on the heating system. That's very much the way it works here. And the idea here is to play with those values by allowing an off period that's a bit longer when you are in the control region. That means when you want to delay the fridge. But of course, you take into account the temperature here and the frequency here. Here that's showing the delta F. That's the thing that the chip monitors in millihertz, deviation from the frequency on the power systems. And then we will use that to decide whether to control, whether to extend the off time. For example, here the compressor has stopped working. When you're in the control region, you might decide to have the off time a bit longer than it would usually be. This has been studied. This has been very close to implementation. There has been UK Grid, which is the UK TSO, done a study to deploy that and concluded that that could save 1 gigawatt of reserve to the UK Grid. So you could do reserve with batteries, for example. So the equivalent of this would save 1 gigawatt. For some reasons, it was not deployed, but it might come back. Some people are really seriously discussing in the UK of making the chip mandatory on every fridge that you would buy. In fact, you will not notice. You would see that your fridge behaves a bit differently when there is frequency differences, but it would be hard to see a difference. Similar studies have been done in the US about air conditioning and heating fans. So the fan is the rotating system that plays the air. A lot of heating in the US, unlike Europe, is air pumps systems. Here we heat wire pipes that diffuse the heat in the room. In the US, you heat essentially with air pump system that blow hot air in the room. And in many parts of the US, more air conditioning than heat. By controlling the speed of the fan, control the power of the system. To some extent, the fan is not powerful enough. It does not blow air into the house. So you're in fact reducing the power system. A similar study in newspaper a few years ago concluded that a huge fraction of the secondary reserve in the US could be provided by air conditioning and fans alone. So some parts of the US, California, are actively deploying forces where you can do now secondary response on your building here by agreeing to modulate the speed of the fans when you receive a signal from the TSO, for example, which means you will heat a bit less or air condition a bit less when there is a need for it due to the grid. This is very similar to the daily task, but instead of reacting to prices, now we react to the secondary control signals sent by the TSO. But the system is the same. We play with the fact that thermal systems have some inertia. So if I have some flexibility in my temperature, the thermal inertia is playing the role of a battery here. If you go one step further, here's an example that was done in Mario's lab dispatch grid with primary frequency support. So you recognize here the Mario Paolone's building. In front of this building, there is a big battery here. You can use such a battery to do what is called a dispatchable microgrid. A dispatchable microgrid is the idea that you could dispatch the consumption part of the grid, not just the generators. In the first lab that we did OPF, we worked on dispatching generators. We said at this point in time, we will dispatch this generator for that power. That's the state of the art today. When we have a lot of batteries that are deployed in the distribution grids, we can start dispatching the distribution feeders, so the distribution grids themselves, which means that, for example, assume you are building a campus or a new eco-quartier or something where you don't do that for a single house because, of course, you need to invest some technology and some management. Then you can decide to participate actively in the management of the grid by publishing a dispatch plan. Instead of being a passive consumer, where you let everything being dictated to you by the utility, essentially you buy a service at a given fixed or variable price. Instead, you can be playing the same role as a utility, or a micro utility. For example, also, if you have solar panels or other means of generation, sometimes also co-generation, heating systems that can also be used to produce electricity, then you are both a producer and a consumer. And then you can go to the market to add to every day of the year to go to the market for what you buy and what you sell. And when you do this, you publish what is called a dispatch plan. For example, you decide that in the green here is the dispatch plan that we should do. That is, you say, here at this period of the day, I am neutral. That means I consume nothing and I generate nothing. Here I have negative. That means I generate some power. Here I consume nothing. And here I import some energy. So you can now do that by going to the market instead of going in through the utility that manages the uncertainty for you. Now you do that, you go to the market. Now, what is the benefit of doing this? Well, the social benefit is that if you imagine a large country, continental Europe, where a large fraction of the local distribution grids are doing this, then that makes the system much more manageable. If there is a peak or if there is any problem, first you will know it in advance. The market will know that it doesn't work. For example, if everybody wants more power tomorrow than there is, gas is not available, then the market will adapt to it. It will force some of the utilities or some of the consumers to not have what they wanted, but you will know it one day in advance, which is not the same as a blackout that comes immediately. Plus, there is a contract. Now you've done this contract and you say, this is what I will do. So it's much easier for the TSO to manage everyone, because now the TSO expects your microgrid to do this. If you deviate from this, when we see the blue line is what was actually done. If you deviate from this, there might be a penalty to pay, or there might be a benefit that you receive, and that's exactly the thing that is given here. You can deviate from this in a cooperative way by providing primary frequency support. Here, the green is what I have published I should do. And now, this is the frequency here of the power. We see, for example, at this point here, the frequency is going below 50 hertz, which means there is deficit of power. Then I see that I produce more here. And vice versa, when there is, so I modulate my actual consumption in order to follow the frequency, which means that we have now a number of microgrids in the interconnection that are helping the stability of the system instead of being completely random things that we need additional reserves to mitigate their flexibility. Here we have a stabilizing effect. How do you achieve this? Well, typically you need resources that are flexible. The more flexible resources are batteries. So here in this grid, there is a battery. but you can also complement the battery with your own demand response system. If you control your own heating systems, then you can also reduce, for example, the power consumption of your heating system. So this is what could be done here. And this is an example of by playing with essentially a battery, but also thermal loads, also PVs. You have your PVs. Now, if there's an excess, of course, the PVs cannot produce more than the sun is giving, but it can produce less. So if there is an excess of power, that is one of the problems we will have in the summer months when with large PV production, then such a grid can forecast what it will produce. If there's any deviation for forecast, it will be the responsibility of this local grid to adapt to and do what really it had forecast and not let the major system go. So some studies have shown that if we have a small penetration, 20–30% of distribution networks have such systems, then there is a dramatical effect on the reserves, and it is in fact cheaper to deploy batteries to do this than to deploy gas turbines, which are the traditional alternative for reserves here. Now let's go to yet another extreme. That's a system that's deployed in France. The company is called Voltalis. And if you go to the website, you can order a device. They call it BluePod, I believe. But they connect to your electrical panel. And that will do a bit like what Roman d'Energie said. When you remember, we can have this interruptible power supply where at most 1 hour, at most 4 times every day, you can be interrupted. Well, this is exactly what this is providing. But this is an independent company. It's not the energy company. It's not the distributor. It's not the energy. It's not the network. It is a special company that provides what is called interruptible load. So they come to your house, on the electrical panel, they put a box that is controlled by a GSM signal. When they instruct your box to stop, it will stop, and they promise that it will be at most 60 minutes per day. Of course, you don't put this on your TV or your light system. You put it on your thermal loads, which are of 2 types. Typically the boiler, like in Switzerland. In France, there are still, because it's a nuclear country, there are still a lot of resistive convector-based heating systems. So this is another one that's also controlled by this here. There is no charge, so it's free for you. You call them, they put that in your house, and you don't pay for it. In fact, you should receive some money, because what you're doing here, you're providing your house as a demand response resource. And the grid can use your house to reduce the total power consumption of the grid. In fact, but they don't pay you anything, but they have, I believe, more than 1 million customers based on the 2 claims. First, they claim that it reduces energy. And second, you're a good citizen, you help the grid. So since it costs nothing and you save a bit of energy, why not do it? So many people do it. In other countries like Canada, the US, UK, there are similar things, but typically there are incentive payments. So you put a box here, and the electricity company or a similar company, in the Canada Peak Savers, the same as Voltalis, will send a signal and interrupt your device. In those countries, they pay you something. Now the payments are minuscule. You get perhaps $50 in Canada a year at most for this. So perhaps here they decided, since the payments are minuscule, you might as well do with that. How does Voltalis make a living? Well, Voltalis goes to the secondary response frequency support market. So Voltalis goes to the French TSO and says, I can sell to you 1 gigawatt of supply, which in fact is not supply, but is a reduction of consumption of 1 gigawatt. So they can go to the market for energy or for secondary response. Well, they say, I can provide you with some flexibility of this here. So they receive money from the market, because there is a market for energy and there's a market for reserve. All those 3 scales of reserve that I showed, primary, secondary, and tertiary, are associated with the market. Primary frequency support is typically part of the grid code. If you connect a generator, you must provide some primary frequency support. But secondary and tertiary are services that you sell as an independent entity. So if you run your battery, your generator, or your hydro power plant, you can use it to sell energy on the energy market, or you can also use a fraction of the energy that you can produce as a reserve that you sell as a reserve here. The pricing mechanisms are different here. TICO is the Swiss equivalent of Voltalis. It's not exactly equivalent. The business model is different. TICO is a Swiss company. They work primarily with heat pumps, and they provide primary and secondary reserve. So this is, for example, a map I took from the TICO website, where they show all the houses that are under their control. So TICO goes to Swissgrid and sells to Swissgrid a secondary frequency reserve, from which they receive money, at least in winter, because in summer the heat pumps are not working, so there's no reserve you can provide. And this is showing, for example, the kind of signal they receive. The black is the black signal that Swissgrid has sent to them, and in blue is the amount of energy that they, in megawatt, that they have modulated here. So here they produced 3 megawatt, which means they have reduced the consumption of the fleet of heat pumps by 3 megawatts. For tens of thousands of heat pumps, it's very small per heat pump, but aggregated over the scale of a country, it becomes not large, but non-negligible here. So in their terminology, they say they implement a virtual power plant. That's a terminology that's often used in marketing literature, which is a bit misleading, but it's used. A virtual power plant means exactly this. It's a distributed resource that has the same effect as a power plant. The effect of a power plant is it's able to provide energy, raw energy, or reserve, control, flexible resource. That's exactly what is provided. I say it's a bit misleading because there's a major difference with a virtual power plant. It's not localized. So you have no control of the effect of this on the grid. In the labs, when we had our microgrid with 13 buses, every generator is localized. So we know with the grid power flow equations, what is the effect on voltage, on line congestion, on power flows of acting on this or that generator. Here we have no clue what happens. When Swissgrid says, increase by 3 megawatt, give us 3 megawatt, we have no clue where the 3 megawatt will come from, which is one of the drawbacks of such systems. They're not localized. That means someone else needs to take care of the possible voltage and congestion problem that might result with other resources. But that is widespread, same with Voltalis, it's widespread, and it has a lot of benefit when it comes, for example, to peak shaving. So expect that next winter, when there will be periods of time where there is a shortage of supply, those systems will be exercised in full to peak, to reduce the power at the peak hour. Here's a more exotic and imaginary richer system, which was developed by IBM for Switzerland. The idea was to use the boilers as tertiary reserve. So all the things we've discussed so far are playing with primary reserve. So we say primary and secondary, which primary acts instantly, secondary acts in the time scale from second to minute with an explicit signal. Tertiary is also with an explicit signal, but has a longer startup time and should last for a longer time. The idea is, if we observe Switzerland and all of its boilers, we have millions of boilers that are heating hot water, then using the flexibility of this is something that perhaps we could control. And the idea to control this is to look at this curve that's showing as a fraction of time the total energy, the integral of the energy that's delivered to all boilers in Switzerland. And we say, well, here is a typical trajectory. This is how boilers work normally. So most boilers are working at night only, but there might be some also that work during the day. So assume that's the typical trajectory that they have. So that's easy to forecast. Now, I can also compute what could be the most aggressive and the less aggressive trajectory I need. For example, I want some amount of hot water replenished at some point in time, typically in the morning. I want this to be available. I can have more because the temperature could be anywhere between, for example, 70 and 80 degrees. So you have some flexibility. And you can decide to heat as soon as possible or as late as possible. So if you can compute those curves here, that gives you an envelope of where the trajectory of your boiling system could be. Now you can, if you can send, similar to Voltalis or TICO, you can send signals to your boilers. You can play with this curve. And for example, if there is, like in the example we gave before, if there is an event where we need to recover from the loss of a big generator, we need a lot of energy. In 15 minutes, we need that amount of energy for 4 hours. Then we can compute whether we're able to provide it. And if we're able to provide it, we say, well, 15 minutes after the event, which is when we are asked to provide this energy, we stop enough boilers. In this case, we stop all of them. So by stopping all of them, if the total power consumed by the boiler was 0.5 gigawatt, then it's the same as if we would be producing 0.5 gigawatt here. Of course, by stopping that, this is our trajectory. We must make sure that we're able later to come back to this point here. So we can ahead of time compute the constraints here. We will not discuss how to do it, but that's very similar to all the programming exercise we've done. You can compute all the constraints and you can quantify how much you can provide for how long in advance. This is what was done in this paper. And they computed and quantified that and found that there was a business model for that. Well, it was a theoretical study, at least at that time, 10 years ago. Probably things like this will also become opportunities in the future. And last, yet another large scale, not large scale, but real scale deployment of this. All the ideas we've discussed here have been deployed entirely for real now, not on simulators or on partial studies, but on an island here, the island of Bornholm, which is an island that belongs to Denmark, off Sweden here, and is, like many islands, electrical problems are more severe in islands. This island is connected to the mainland, here to Sweden in this instance, by a cable, but this cable, for some reason, is often cut. It's in the bottom of the sea. The Baltic Sea is very shallow, as you may know, and sometimes there are fishing boats or Russian submarines who come and break the cable. So this cable is often cut. And that's one of the major problems of this island. It's plagued with power cuts here. So people in this island were trying to have autonomy. Now, because it's Denmark, they didn't want to use fossil fuels. So they decided to try to use all the possible recipes. So wind energy is the main major supply they used here. But this is a diagram of the production of the over a period from January to May of the production of wind. So that's exactly the reality of wind energy. So you see there can be periods of several weeks during which you produce a lot, but there can be also periods of several days during which you produce zero. And if you take the integral of this, you will take that the average is more close to 20% of the peak than 90%. So wind energy has an average that's very low compared to the peak. So that's one of the worst in terms of grid here. It means that the variability is huge. They also have a coal plant, which is not very green, but is historically there. And they found out that with those numbers that they have here, so peak demand 55 megawatt, supply 30 megawatt, wind turbines 60 megawatt, but as we know, that's very volatile. So in average, if they get 20% of this, they don't even break even. They found that by doing demand response in homes, they could provide 3 megawatt of capacity in winter. And they also did what is called positive demand response, because the wind energy sometimes is producing too much here. So they did a bit like David McKay's system, but not with price, with immediate signals sent to the homes. When there's a lot of heat energy produced, then the heating systems receive a signal to increase the temperature. So your house is a bit warmer simply because there's more wind. And if you keep your windows closed and the house is relatively well insulated, that will allow you to consume less when the wind goes away. And they found that they could avoid 3 megawatts they could reach 3 megawatts, the equivalent of 3 megawatts of supply through demand response. It gives us something that's relatively stable. You see that the power demand is 50 megawatt, 3 megawatts, so we are less than 10%. That's the order of what demand response is able to give to you. Of course, demand response is not any physical quantity. Demand response is only control and communication. So that comes for free in terms of resources. So roughly 5 to 10% of the consumption of a grid can be saved by intelligent management and demand response here. Voilà, I think it's time to do a break. So let's break. The last example we will see, which is not yet very significant today, but we hope will be significant in the next decade, is electric cars. So major change in mobility patterns and in the electrical grid is the presence of electric cars. We consider that if we replace all thermal cars engines by electric cars, the increased consumption on the grid will be order of 30%. I've seen different, again, 30%. It's different numbers depending on where you see, what you see, but that's order of what it means, which is huge. I mean, the electric grid is not like the internet. You cannot put in the internet if the communication need increases, you put more optical fibers, more switches, more routers, and bingo, the problem, more 5G or 6G antennas, and then the problem is solved. For electricity, there are physical resources that are limiting, in particular on the generation side. So that will be a major issue. This has been recognized in the literature. There's the generation side, of course, but there's also the grid congestion side. This is a typical example that was studied in this paper. So all references to such papers are at the end of the lecture notes that you can print. This is showing congestion of the lines when people start charging their electric cars. In fact, if you don't heat your house with electricity, if you buy an electric car, you will probably multiply your electricity consumption by a factor of 3 to 5. Right? Because today, with the lighting technology that we have, even if you watch TV a lot and you have a washing machine, but the integral of that is relatively modest compared to what an electric car would consume. You aggregate all of this on a distribution network and you find problems like this one here. Here, those are problems of congestion. On the x-axis is the penetration of houses that have an electric car. So you see it's even relatively small. 30% is considered a high value. But it's quite possible that in 10 years from now, we will even have more than 30% of cars that are electric. So we might be above this. The measure of congestion here is the power loss here. So you see that the power losses on the grid today are, or on this grid here, in the worst case, are close to 5%, which is already a high power loss. This is the absolute maximum for most operators here. And you see that when you start having electric cars, you go beyond. On the worst case, on a winter day, you might go to 10% loss, which means the ampacity constraints of the lines are probably violating or the lines of the transformers are violated. There's congestion, too much current, too much power transferred on the line. That's, as you show, that's not everywhere. It's not on every feeder. It depends how the lines are. typically when you build an electrical grid, you dimension it with some assumptions. For example, if there is a factory here, you make a big grid. Perhaps the factory disappeared 10 years ago and the grid is still big. So sometimes you build a grid here with some assumptions and then you double the population and the grid remains the same. So there's a lot of variability. It's not everywhere a problem, but it's a problem, I would say, in about 1/3 of the distribution grid, according to what we read in the literature. What is the solution? Well, the solution is to do smarter charging, for example, doing MPC-based charging, like we saw for the house, for David's house. If we signal either through price mechanisms or through some other systems, we can signal to the car charger some instruction to avoid this excessive consumption. This is what was done in this paper, where they assumed an MPC style type of things, where we, a bit like a dispatch problem, we schedule the currents that every car can have. That's an extreme case. It's not quite clear how it can be done, but there are other techniques that have been deployed. For example, another one is to have a smart electric car charger that reacts to signals that can be either local signal of congestion or can be an external signal sent to you by an aggregator that will model the grid and try to avoid this problem. Very much like we did in the lab. If I have a model of the grid, I know what are all the consumptions along the grid. I can decide for a max power that you can reach here. Which would mean that perhaps if you want to charge your car at full power, perhaps it's not possible, or perhaps it's possible only on a high power charger that might have, as we mentioned before, a high peak power, therefore a higher price of simply being connected to the grid. So you might need to choose whether you want to connect your electric car with a very high power charger and or a charger that is susceptible to that. Some such chargers exist already today, so they receive signals from the operator that may, very much like your boiler, may force you to charge at lower power. Voila, that's the panorama of all the demand response efforts that are booming today, and many of them are, in fact, business opportunities. Many of them are things that are emerging now. Let me ask the following question. So if we go back to Voltalis, who is one of those startup companies that lives on demand response, they don't pay or charge anything to consumers, but claims that consumers benefit by seeing a reduced electricity bill. Do you think this is true? I close the poll. Closing. We see a short advantage to B. No, there cannot be any reduction in total energy consumed. Well, let's postpone the answer to this to a few more minutes when we will do a few chapters of theory, and we will see what's the true answer, because the French Energy Agency has studied this case, and there is an answer to this. We'll see what the answer is. So the majority believes B, so it believes it's a fake news, right? The statement of Voltalis is fake, which is, we'll see what the truth is. So what we will do now is provide a few elements of the theory that's behind all the papers we've discussed and what's behind of the understanding that people have of demand response, or the beliefs that people have about demand response. Demand response, in fact, like all the energy market, is based on the following small economic model that we will discuss now, which is the concept of demand and supply curves. So on the user side, it's based on the assumption that's very frequent in classical economy, that we believe that users have a function. This is called the utility. Q is the quantity of energy I buy, let's say over a 15-minute period, and use the utility I attribute to this. That's a myth that economists have made very popular. We react as utility optimizing animals. That's one of the very simplified models in economy. We will discuss, well, this is used and we will discuss the limitations. And of course, in reality, what is this utility? It's very hard to quantify, but in some cases it can be. Here are three examples of such utility curves. So on the x-axis, I'm plotting Q, the amount of kilowatt hour I'm willing to buy in a given 15-minute period, for example, and use the utility I attribute to this. Here, this is if I have completely non-flexible. For example, us here, we need the light, we need the beamer. If we don't have it, we're not happy, we cannot do the lecture. If we have more than that, it doesn't bring us anything. So the utility we have is zero if we don't get what we need, and is the value we have of being here together if we get it. If we get more, there's no benefit, there's no added benefit. So that's what we have when we have a total inflexible thing. The theory often assumes that we have something like this, a concave curves. So it's increasing, that means if I get more, I see more usefulness, but the returns are diminishing. There are so-called diminishing returns. Diminishing returns mean that the function is concave, the derivative is decreasing, or to put it another way around, when you have very little at the beginning, it increases very fast. Then once you have a lot, giving a little more is good, but doesn't increase your utility very much. I'd say that's the classical type of function that's associated with this theory. And then sometimes you can have something perhaps more like this for in the context of electricity consumption. There's probably a minimum that you need. Below this minimum, you feel there's a blackout. You need the light, the heating system, a number of a minimum power for your computer, your light, everything to work. So below which you're not happy, after which you have some utility. And then if you have more, perhaps you can do more things. You can play games instead of just watching TV or things. So that is, I would say, a classical function that is given also. That's the consumer side. The economic theory of markets and demand response in particular uses also a similar thing for the supply side, where in contrast here we have the amount of energy that a given generator is willing to produce at a given price. Here we can have an inflexible provider, for example, a wind provider that produce, once you have your wind turbine that's in place, here we're ignoring the investment cost, it's just the operational cost. Once it's in place, I can produce Q1. If I produce Q1, the cost of doing that is zero to me. If you ask me to do more, the cost is infinite. So I have zero cost below Q1, infinite cost above Q1. That is typical of renewable energy, where there is no fuel being consumed. There is only capital investment, and it produces some quantity at zero marginal cost. Now, if you have a flexible supplier, typically that's what the theory likes to see, we have a convex curve. We're able to supply more if you ask for more, but the more you ask us to do, the more it costs. For example, a diesel generator, if you want to run it more, then at higher speed, it will be less efficient, so it's able to produce more, but the cost in terms of liter of fuel per kilowatt hour produced will be higher. Something ideal here with a fixed capacity is given by this curve here. Here, that means the cost is constant, so it's a completely well-managed system, completely optimized system with a capacity. It cannot produce more. If you ask it to do more, that's what you will have here. Yes, question?
I find it counterintuitive that it would be complex because the costs are usually high for turning on, and then if they produce more or less, it's not.
So here, that's a good question. The cost is higher for turning on. Here, this theory ignores the startup and shutdown cost. So those are just the costs, C of Q, that we had in our OPF exercises. There's no startup or shutdown costs, which is a good point. That should be added also, but let's just look at the basic theory. Here, it can be linear if you have constant cost, but typically with a maximum, which is all, here is a convex curve. And if you want an idealized convex curve, that's easier to analyze. You typically have something like parabola. Now, what will the generators do? So the generators, typically, the generators are companies. So companies do optimize their costs, unlike users don't optimize the utility. Here, what a generator will do typically will say, if I ignore the startup and shutdown costs, I have the capability to generate Q at a price C of Q. Which quantity will I generate? Well, the answer is I want to maximize my revenue. If the market price is P, I will receive PQ. Well, one specificity of the market price that we discover these months with the shortage of gas and oil is that the price is the same for all. Once the market price is P, you pay P for every kilowatt hour that you buy, not just the last one. So if I generate a quantity Q, I will receive a payment PQ, and I will pay PQ minus C of Q. So my problem is to optimize this. I don't want to generate as much as possible or as little as possible. I want to receive as much money as possible. This is how economical actors react. So their goal would be to maximize this. Now, the supplier maximizes this. Well, similarly, at least this is a bit more fictitious, we assume that the consumer also maximizes its utility minus what it has to pay for. The consumer pays PQ for a quantity Q and receives a utility U of Q. Therefore, in this ideal model, it will maximize the happiness or the utility that you receive minus the price you pay. If the function U is smooth, has derivative, and is then that means at the optimum, we will have the derivative of Q will be equal to P. So we will consume a quantity Q that is given by this equation. Given the price, if the market price is P, how much will you use? So you have smart meters at home, the price is P, you are a smart user that follows this theory, the quantity you will consume is given by solving this equation. This is a bit theoretical. What is less theoretical is the producer side really does this. The consumer side will do the same. It will maximize PQ minus CQ. Therefore, it will solve this equation. Derivative of the costs with respect to Q is equal to the price here. Now, many producers will really do this because they're in business of doing that. This is why what is called the demand curve and the supplies curve is in fact the derivative of the utility in case of supply of demand and of the cost in case of supply here. So I plot here for a user the derivative of the utility. We said the utility function is typically concave. That means the derivative is decreasing. For a smooth function, that's a characterization of concave function. The derivative is decreasing, which in economic terms is also called diminishing returns. The derivative being the delta utility divided by delta Q. Similarly, the supply curve corresponds to the derivative of a convex function is increasing here. So the theory says if there is a free market, all consumers go to the market to say how much they want to buy. All producers go to the market and publish how much they want to sell. Then if the market is working, it will stabilize at a point where the price is the same for both. That's the definition of a market that works. There is a common price for everyone. And the price will be such that the quantity that is produced is given by if we take P, the quantity Q will be solving the equation demand curve versus P versus Q are on the demand curve. They are also on the supply curves. That means the point where the market will stabilize is at the intersection of the aggregate supply curves and demand curves. So we take the sum of all the supply curves, the sum of all the demand curves. The point where they intersect will tell us where the market will operate. It will tell us two things. It will tell us the price on the y-axis and the quantity on the x-axis. So that's the theory that's behind the way the electricity grids are run financially. Like anything in economy, contrast to grid. In grid, we have equations of the grid, and we know they're physically rooted, and we know it gives nasty OPF problem, but we know they are real. Here in economy, this is models about how people behave, so they're more or less real, but they are real in the sense that the electricity markets are using this system here. Now, a market does not always work. For example, there might be market collapse, for example, if there's too much demand and not enough generation, and the curves are not all smooth, but have those minimum or maximum that I mentioned before. If everybody has a minimum Q0, and the sum of all the minimum demand is larger than the sum of the maximum production, then that's an obvious way where the market will collapse here. There might be also inflexibility, startup costs, and a number of other points here. So the way the grid is run in most countries that are not so-called vertically integrated, that means all countries except perhaps China grid, are by having a market where a day ahead, all producers go to the market with those demands and bids. So the suppliers do the supply curves, that's the companies that run power, hydro plants, nuclear plants, etc. The demand curve is for those distributors, sometimes it's the same company. And also if you run your dispatchable feeder, that's exactly where you will go. You will go to the market here and try to agree per 15-minute time slot on such a value and a price here. When this does not work, this is what the TSO, transmission system operator, is also here for. The TSO may adjust the market to add some more generation if there's not enough by calling some reserves here. Also, there are so-called additional markets that are capacity market. All this theory here uses only operational costs, just the cost of running your generator or the benefits for the user. Of course, if you do only this, you have a problem. This problem has shown up, for example, in some countries that have liberalized the electricity sector. There is no incentive to invest. If you invest into a generator that has a high price, for example, and will be used very seldom, then it's not interesting, so you will not do it. But we need it, because perhaps when there will be a peak or a failure somewhere, we will need this generator. So we need some reserve for the stability of the system. So there is a so-called capacity market, which is related to the secondary and tertiary reserve. When I offer a reserve services, I mean offering a capacity, not an energy. I'm saying I have here a generator or a demand response system that's able to generate 1 gigawatt, but might not generate it if you don't call me. For this, of course, I need to be paid. It's like a medical doctor who has to be on piqué, on duty. You can call the doctor during the night. Of course, that medical doctor gets paid for being on duty and being callable, even if you're not called. So this is exactly what needs to be added and that we don't discuss in this presentation. So let's check our understanding of the demand curve. Here I'm showing 3 demand curves. So demand curve, right? So derivative of utility. One is an inflexible load, one is a flexible load, and one is what we call a bid-dependent load. Well, that's what we could call an optimizing consumer that says, if the price is above some threshold, I'm willing to reduce. Which one is which? I close in a second. Majority says C, which is the correct answer. The inflexible load had the utility 0 and infinite, so the derivative, at least in a crude approximation, would give this. That's the classical elastic load that's in the imagination of many system modelers. That's the reality of something more concrete here, bit dependent loads. That means when the price here is increasing, my utility doesn't change until there is, when the price goes above this, I'm willing to drop the quantity that I will be consuming because I'm sensitive to the price. That's what we hope happens when we do demand response with users that will use some flexible loads here. This is exactly what is shown in this paper that I mentioned. Here is, for example, an example of demand curve. That's an analysis, that's the kind of analysis that's done by the people who run the markets to simulate what will happen. That's the supply curve. Oops, I have an audio interference here. The supply curve, and that's the demand curve, the traditional demand curve, when we have very little or quasi no flexibility here. So you see it's an inflexible, it's quasi a straight line. And the only thing that can change is the amount of the Q0 that people want, depending if it's a cold day or a lukewarm day in winter here. And then you can see the impact on the price here, on the electricity price, by looking at where we are on the supply curve here. Of course, if there is a power outage, which will shift the supply curve somewhere, for example, the nuclear plants in most countries are considered cheap production because their investment cost has been, at least for the current generation, the investment cost has been amortized. Next generation is another story. If we lost one of them, the supply curve moves to the left, and we see that the same demand curve can lead to very high prices here. This is exactly what happened in Texas. This is also what can happen in other places when it might happen this winter as I said, has already happened in Spain and other places in Europe as we have this supply curve that becomes larger. Well, if we replace the demand curve by an inflexible demand curve by something that is more flexible, so ideally we replace the black curve by this red curve, then we hope to be able to maintain the price here. So the trick of engineering the demand response will be to do it in a way such that we manage to have a price here, a low price here. So by playing with demand, we can manipulate the prices and avoid the problems. Instead of having everybody pay a lot, we will have everybody do a lot of demand response, which may mean having your Voltalis and other TICO and other systems manipulate your system here. Similar things have been observed here when we have, that's the Norway experiment that I said we would describe a bit later. These are the original demand curve. Now, if we shift everything, we have simply this change here. But if we introduce some more flexibility, where we say, depending on the price, we may or may not use that much of the energy, then this is the curve we will have that will now have a significant impact on the price here in the different areas. I mentioned that the utility curves are a bit mythologic. The supply curves, sometimes they are not here. That's the demand curve for industrial customers. That's an example done from a utility in the US. Now for industrial customers, not for you and me at home, but if you're running a factory or a big building, then you can start putting a price tag on what it means to you to have more or less electricity. because then your utility is not like for us some vague feeling, but it may have to do with other measures you need to take. For example, you may need to shut down something, which means you lose a revenue because you don't rent some office space or things of that nature. So people are able to provide at least rough ideas of the curve, and that's the kind of curve that this utility, for example, this is Georgia Power, was able to obtain. So they do get this thing here, which allows them to dimension exactly their demand response program. We've seen already an example of customer side of demand response. So that's if you run a building to react to price. We see here that when the price is high, we have zero consumption. But we have a pre-bounce effect here, anticipative bounce before the high price, which is one of the effects accounted for. This has been recognized in this recent paper 2 years ago. The economical theory of demand response said market price stabilizes where the curves intersect. In fact, this is a gross approximation of what happens in reality. In reality, here is what happens. This is showing total power as a function of demand responsive. So we see here there is the average power is consumed by the population, the US population. Remember that playing with fans could reduce could provide 70% of secondary reserve. Now here is what happens in reality. So that's the average hours that this population of appliances would use. So here it's not fans, it's water heaters that are slow of fast fridges and pools. That's, I believe, a study in Florida where that, so there's particularly swimming pools and each swimming pool has a system to clean it, and that uses a bit of electricity. So it's like fridges. Every pool individually is not a lot, but together it's a huge resource. We see that demand response is visible here, but we see the pre-bound effect before, and we see also some effects that it gets, first it dies out. If you instruct people to reduce their energy consumption, they can during 1 hour, 1 hour and a half, but after that, not really. And as soon as you remove the demand response signal, then there is a peak. So that's the reality. Pre-bound, post-bound, and fatigue here. Worse, some demand response program can increase diesel generation. For example, TCO, why is it? Well, because when you do demand response, you rely on something very stochastic that depends on the weather. If you are TCO and you're selling to Swiss Grid a reduction in power in heat pump, when in the summer or now, nobody's using their heat pump now for heating their houses. So you cannot reduce. But in order to participate, to provide a service to Swiss Grid, you have to provide the service with some guarantee. Perhaps Swiss Grid needs the service now, even though now there's not a peak period, but perhaps a nuclear plant will have to shut down. Perhaps there's another problem somewhere. We lose a line with Italy or whatever. So we might need an emergency secondary response event. Therefore, you need to be able to support it. So the TCO solution is to buy hydro plants. So TCO has bought a 1 megawatt hydro power generator to be able to provide demand response in case the heat pumps are not able to give such a response here. So TCO is Swiss, so they do it green to be able. Others are less picky, and they do demand response program. And similarly, the one way to do a demand response program is to sell primary or frequency support. The clean way to do it is to have a battery, like I showed some examples. The unclean way is to have a diesel generator. So if the Swiss Grid says to you, now you should give me some generation, then you have a diesel generator to provide it. So some demand response providers do that. Now they claim that in average they use it so little, it's still good. But that's some of the things to be aware of. I will very quickly talk about elasticity. So when you design a demand response program, some papers are mentioning these pre-bound effects, right, that are illustrated here. Here I'm showing in gray the load that exists as we measure it before introducing a demand response program. In red is what we hope when we have a demand response program. We would like to shave that peak here. So we would like to smooth here. Of course, we expect that what has been delayed will be visible here. But in reality, perhaps what we will obtain is this. Right? We'll have a peak after that. And that peak might be as bad as the peak we were trying to avoid. That's clearly the thing you want to analyze before deploying a demand response program here. So that's the bounce effect. So that has been captured by this paper here that uses the concept of cross elasticity, that is saying essentially that how much load at time S will be moved to time T due to a change in a price at time S here. So if we reduce or augment the price of electricity at time S, the load at time T will be increased, and there is effect on the load at time T to every time at which we've done a change here. It's assuming it's lossless model. That means the only thing that demand response is doing is shifting, anticipating or delaying the consumption, but not changing it. That's the assumption in this study here. And that gives this model here, the variation in load at a given time T is the sum of all these changes due to price differences at times before and after. Now, the study has assumed two types of behaviors. Inflexible behaviors, those are customers who do react to the time change. Remember this Norway study where your washing machine becomes very expensive between 6 to 8, so you don't use it. So you reduce your consumption from 6 to 8, and you put it equally before or after. That's what is called inflexible customers here. And here, an optimizer customer is one that spreads it very evenly before and after. Right? So most load is transferred to early and late hours of the day, independent of when the event occurs here. So that's an optimizer behavior. And they have studied the effect on the market price when there is a loss of generator. So as we've seen, that's one of the motivation for doing demand response is to reduce the consumption when there is a peak that is due, for example, to a failure here. We see that we find in blue the expected prices here. If there's a loss of one generator or shortage of fuel, like is happening now, those are what the prices become. So the pink prices are the prices that we would have if we have the loss of generators. And the yellow and the green prices are the prices that result in this model, depending on the type of customer. If we have inflexible customers, so customers that simply shift 2 hours before and 2 hours after, we see essentially that the benefit is not so large. We do reduce the peak here, but we increase it after. So we need consumers that really shift very wide apart and really consciously send it to the periods of the day where the prices are extremely low here. So this is illustrating that, well, simply shifting demand works in theory, but in practice, you might need a lot of fine-tuning to make it optimal here. The last point that I will discuss is to bring us to the solution of our quiz. Is Voltalis diffusing fake news or is it real? So the term is called loss of load. Loss of load is the fraction of energy that is saved due to demand response. If there is pure shifting, the loss of load is zero. So here I'm showing a hypothetical example where we have the natural load that would happen before receiving the signals instructing us to change our behavior. And the integral of this is the consumption I've done. Now, when there is demand response, I reduce now, but there is a peak after. And the question is, what is the difference? If E1 is less than E0, there was a loss of load. This is what Voltalis claims. Voltalis claims that putting this box to you will cause a loss of load. This is why you will pay less here. So is it true that demand response saves energy, right? Well, that's related to yet another question. Assume you have a house that you're fortunate enough to have a vacation house that you visit not so often. And then one of the fundamental questions there is, when should you heat? Right? Should you ask a neighbor to come and heat the house one day before you come so that the house is nicely warm when you come? Or should you keep the heating on at all during, for example, if you visit it only during the weekend, should you keep the house warm? Because the cost of heating it is also large. So what is best? Should you keep your house warm or should you not? Same thing for your apartment. When you leave for your vacation in winter, should you keep your heating on or should you switch it off? Right? When I am away, I interrupt heating. Does this save energy? So I close the poll in a few seconds. Majority says A. Yes, there must be a reduction, which is true. We will see why. But if you think about it, that means Voltalis is right. There must be a reduction in heating. Now, with heating and thermal systems, we need to be very careful. There's a large variety of things. It depends on many things. The coefficient of energy of the heating system is constant. The answer is yes. And we will see why in a second. Now, we'll talk also about those details here. So first thing is to realize this is not the same question as the rebound effect. The rebound effect is the fact that there will be more later. And that is certain. The answer is yes. If you stop heating now, you will heat more later. That's for sure, because the temperature will drop. In order to get back nice temperature, you will need to heat up later. But that's not the question. The question is, if you keep your house at a constant temperature always, is it more efficient, or should you let the house cool and then heat up just before arriving? Right. Well, we have the answer in the house model that we use for the MPC. That's the house model, if you remember, that says that the energy I put into the house goes into two places. It leaks and it goes into inertia, which we can visualize with the physical equations of a leaky bucket. A leaky bucket, for those of you who took the advanced communication course, that's a model used also in deterministic networking. A leaky bucket is a bucket of fluid here that does a leak. And so you need to constantly pour things into it, otherwise it will be empty here. Hopefully the leak is small, so you constantly put fluid into it. And if you write the equations of the leaky bucket, that will be exactly something like this, where the temperature of the house is the amount of liquid in the bucket, the height that you read here. Because you put heat here, some of it is used to increase the temperature, that's the inertia here, and some of it goes away. And the speed at which it goes away is, of course, depending on the outside temperature, which is not shown here. Which we can, of course, put in integral form. Now, let's compare the two scenarios where I don't interrupt the heating or I interrupt the heating. And here I'm assuming the problem is cold. We are in a cold weather and we want to heat. So it's a chalet in the Alps in winter here. So when I have no interruption, the building temperature, T star of T, is no interruption. The building temperature is equal to T star of T, the optimal temperature always. I keep the thermostat to 19 degrees all the time. So the total energy I use is the integral of this, where you see the building temperature is T star here. Now with the interruption, the temperature T will drop. If I stop the heating, the temperature will cool. And now there is a nonlinear effect, is that what happens when the temperature is lower? Well, this is illustrated here. So on the left is illustrated what I do when I keep the temperature constant. Every minute, I put enough heat into my house such that the temperature remains constant and part of it goes away. Now, if I stop heating, this is what happens. I stop heating. So I stop putting temperature energy into my house. And then the temperature drops here. At the end, I will need to put more heat. That's the rebound effect. However, all the heat that I see here, the temperature here, is equal to everything I've put into minus what has gone, plus what was initially present. That's fluid system 101. If you think of it as water, all the water that's present here is the water that was present here, plus the water that has been added, minus the water that has leaked. That's right. Now, what's the difference between the two? In terms of leaks, what can we say? What is the difference? Yes? Yes. Well, it's still leaking here a bit. It doesn't leak anymore here. Even in between, so you're right. So even in between, the leak will be less. Here, the leak is proportional to the difference between outside temperature and inside temperature. So if you keep your building warm at all times, then it leaks more than if it's cold. In fact, when it will, if you wait it long enough, it will settle to the outside temperature and the leak will be zero. So the difference between the two is that the leak here is higher than that. Now, if we compare the two, at the end, I assume I have the same temperature. I want equal comparison. I've done a rebound effect here to reach the same temperature when I arrive. So this temperature is the same. The leak here is less. Therefore, here, the heat, the total heat is less also, because there is balance. Total in minus total out is equal to this plus this, which is I start from the initial, is equal to that. So if the leak is less and the final temperature is the same, it means that the heat we've put here is also less. The integral of the heat is less, which is simple to understand. In fact, what we do when we keep our chalet warm, we constantly keep the walls at the high temperature. That doesn't cost anything, but we leak. We leak more because our chalet is warmer. The inside temperature is warmer, so we leak more than by bringing the temperature down. And all the temperature we will put here, we would have put it there anyhow, and more. Yeah. If you do it multiple times, well, the point is during every period of time where the chalet is empty, it's better to let the temperature drop. Of course, this is assuming a number of linearities in the system. First, I can heat the system here 3 times more. Perhaps I cannot if I have constant power or small power. Perhaps I cannot, but then you need an MPC to start heating a bit before, but the result will be the same, will be more advantageous. Here still, we're assuming the coefficient of efficiency is constant. Here I'm talking of the amount of heat. Now we see perhaps here, I want to heat a lot during a short period of time, and perhaps to put 10 kilowatt hour of heat within 1 hour costs me much, much more raw energy, kilowatt hour bought from the grid, than doing it at a very slow power. Because the coefficient of efficiency of a heat pump, for example, is not constant, if you want to generate high temperature water with a heat pump, it is much less efficient than if you want to generate low temperature, lukewarm water. So there might be things that change that a bit. If that costs a disproportion, you might lose here what you had gained here. So I'm not saying this is absolutely always true. Certainly it's true if you have resistive convectors that translate with quasi 100% efficiency, the electrical power to heat, then certainly this is true. Now let's return to our statement about Voltalis. As I mentioned, this has been studied officially by the French energy, whatever it's named, the agency that's the government agency that's in charge of monitoring what happens in the energy sector, ADEME. So they've examined Voltalis, and they found that it's not a fake news. They found that it's true that that saves close to 10% on heating, but no significant saving on hot water. So for the boiler, you let Voltalis do it. It doesn't cost you anything, but it doesn't bring you anything either. For houses, it does. How do you interpret this? Closing in a few seconds. And the majority says B. So does someone who said B want to explain why? Correct. That's also my interpretation. That's what is in that report. Boilers tend to be well insulated. It's a completely very localized system that fits in a small space and is well insulated because it's made to be boiled hours in advance. So the leakage is small. Of course, there is some, but it's small. And of course, those are based on statistical data. So there is some uncertainty around it. So boiler leakage is small. So if you defer the heating, if you heat a bit before or a bit after, we saw that the difference comes from the leakage. It's good to let the temperature drop because there's less leakage. But if the leakage is negligible, whether your hot boiler is full of hot water 6 hours before you use it or 24 hours before you use it, that will not make a lot of difference. Yes?
It's also the fact that water has a heat capacity, which is way better, like it heats up way better than air, and it's going to have this thermal inertia, which is going to keep it warm. Like air is going to cool down.
It's true, but heat capacity is not the same as leakage, right? So heat capacity means it takes much more time to make the thing warm. It doesn't mean leaking is another thing. Leakage and capacity are two orthogonal issues. Right? A big stone house has a huge inertia, big capacity, but the big stone house has also a huge leakage. So it takes a lot of time to heat it up. Once it's warm, it feels warm inside because the walls have stored such a huge amount of heat, but they leak a lot. You need a lot of energy to keep your stone house warm. The difference is if you stop heating your stone house during one day, you will not notice anything because you have all this heat that is stored in the walls. But still, it's leaking. So the effect of leaking is not visible if you have huge capacity, but the leaking might be the same with huge capacity. So there are still two orthogonal issues. Now, what is believed is that that's the reason. Boiler leakage is small because boilers are well insulated, whereas houses, except for very modern houses, and modern houses are not customers of Voltalis because they don't use resistive heating. So the houses that Voltalis has as customers are houses that have resistive heating, probably not perfectly insulated. Therefore, the leakage is present. And if you reduce the temperature, you reduce the leakage, so you feel a difference, and this difference has been quantified to 10%. Voila, so that was all about demand response. The lecture today was a bit different. We've spoken of things that are perhaps more mundane, more in flux and in progress, but this is to make the liaison between the hardcore theories we did in this course and what you will use of smart grid in practice. This is a vibrant domain where lots of companies are emerging, are doing all those things. Some of those will survive, some will not, but that's the fun of it. Here I'm giving a few online resources for demand response. So in summary, it can be seen as a form of virtual electricity storage, which has a lot of benefits and a lot of drawbacks. The main benefit is that in terms of resources, it costs only computer and communication resources, which in terms of energy is minuscule. You don't burn fuel when you do demand response, right? But of course, it's less flexible in the sense that, for example, if you TICO has no, when the heat pumps are not heating, then it has lost its flexibility. So that's in the constraint of things. Batteries, pump hydro, compressed air are alternatives, and they are competing. And so there is a gray zone between the two, where some can use what the other is doing, and but not always. So the future will say there will probably a mixture of all those elements to control the grids optimally in the presence of a large penetration of renewables. Demand response can act at all the timescales that we've mentioned of primary, secondary, and tertiary reserve here. And those are the references for all the papers that I've given in this lecture today. Voila. Thank you very much. You're well equipped for the rest of studying the grid, and I hope you will contribute to making the energy future of our countries better.